Welcome to the deep dive. Today, we're diving into some research you sent over about generative adversarial networks, or GANs for short.
Okay.
This paper, it's got a pretty interesting title. The GAN is dead. Long live the GAN. A modern GAN baseline. Um, Before we get into all that, though, can we
Yes.
just back up a second, make sure we're all on the same page about what GANs are? For anyone tuning in who maybe hasn't, lived and breathed GANs like
Yeah.
we have.
Yeah, sure. So at their core, GANs are this type of neural network,
Okay.
and they're designed for the purpose of generating new data.
Okay, so think AI-generated art.
Exactly. And the way it works is kind of like a competition. You have two networks. One's called the generator, the other's a discriminator.
Yeah.
The generator, it tries to create this, this data, could be an image, could be other things.
Mhm.
And the discriminator is trying to figure out, is it real or is it fake?
Got it.
And so as they train, as they go back and forth, the generator gets better at making realistic stuff, and the discriminator gets better at spotting the fakes. And this adversarial process pushes both of them to improve.
So it's like a constant game of cat and mouse,
Yeah,
right?
exactly.
Like they're always trying to one-up each other. And this is the tech behind all those, crazy, realistic deep fakes we see popping up online, right?
That's right. Jandies have been this huge driving force behind all the crazy stuff we're seeing online. All these realistic and creative AI-generated images, deepfakes, the whole 9 yards.
Yeah.
But they've also gotten this reputation for being, well,
Difficult.
yeah.
Hard to train.
Right.
Complicated.
Right, like really finicky, and that's what this paper is pushing back on.
Right, exactly.
Because they're saying, hold on a second, maybe it's not the GANs themselves that are so tricky. Maybe it's how we've been building and training them.
Yeah. They're saying this perception that GANs are inherently difficult to train. It comes from, us using outdated architectures
Okay.
and relying on all these little kind of hacks and workarounds. They call them empirical tricks. Okay, can you give us an example? Like, what's one of these so-called tricks?
Sure. So you've probably heard of GAN.
Yeah.
It's a pretty popular GAN architecture. It generates these really high-quality images.
Yeah, some really impressive stuff.
But to make it work, they have to use a whole bunch of techniques
Okay.
to address certain issues, like, mode collapse, for instance.
Right.
So one of these techniques is called gradient penalty, which basically tries to stabilize the training process by penalizing the discriminator if it has, really steep gradients.
Okay.
And then there's another one called mini-batch standard deviation. That one encourages the generator to produce more diverse outputs.
Okay.
But all these things, they can end up making GANs really complex, like this big tangled mess.
Yep. It's like trying to fix a leaky faucet with duct tape, right, instead of actually, fixing the pipes.
Exactly.
So you mentioned mode collapse.
Mhm.
Can you break that down for us a little bit?
Yeah.
What's actually happening when a GAN experiences mode collapse?
So imagine you have this GAN, and it's trained on, this huge data set of faces, all sorts of different faces, right? Different skin tones, hairstyles, the whole works.
Right.
And then the GAN starts to experience mode collapse. It basically gets stuck, producing only a very narrow range of outputs.
Oh.
So instead of generating all those different faces it was trained on, it might only generate, say, faces with blonde hair and blue eyes.
So it's not really capturing the full diversity of the data.
Exactly. It's like an artist that can only paint one type of portrait no matter how many different people they see.
Right. Not very useful if you're aiming for true creative expression.
Right.
But this paper, they claim they found a more stable, reliable way to train GANs.
Yeah.
And they say it actually eliminates the need for all these workarounds and hacks. So what's their secret sauce?
Well, they've got this new approach that uses a specific type of GAN loss function. They call it relativistic pairing GAN loss, or PGN for short.
R3GAN. Okay.
And they combine that with two different types of gradient penalties.
Okay, I'm not going to lie. Some of this is starting to go over my head.
Yeah, no worries. The math can get pretty hairy.
But the key takeaway here is that this new combo, it leads to a much smoother and more predictable training process,
Exactly.
which basically sidesteps all those pesky issues like mode collapse.
Right. It addresses the root of the problem instead of just patching over the symptoms.
I like it. Okay, so far so good. But you know me, I always love a good concrete example. Can you give me something specific from the paper that really shows how effective this new approach is?
Sure. So one of the coolest things they found was by using this new loss function, they were able to get pretty much the same performance as R3GAN,
Okay.
but without using any of those extra bells and whistles.
So they got rid of all the bloat, and it still worked just as well.
Yeah, pretty much. They were able to simplify the whole training process and still maintain, maybe even improve the quality of the images.
Okay, that's impressive. So they're saying, hey, we can make this whole thing simpler and get even better results. Now, it sounds like they didn't just stop at improving the training process. They went ahead and revamped the whole GN architecture itself, right?
That's right. They wanted to make the whole system more streamlined, more efficient. And they call this new architecture R3GAN.
R3GN, interesting. Sounds like a whole new era for GANs. So how they go about modernizing this architecture? Did they start from scratch? Or did they take inspiration from some existing models?
They actually took a really clever approach. They started with R3GAN 2, which is like a souped-up version of R3GAN.
Okay.
And they basically went through and systematically stripped away anything that wasn't absolutely essential for performance.
Oh.
It was like decluttering on a massive scale. They removed anything that was just adding complexity without significantly contributing to the results.
So they basically Marie Kondo'd the whole thing, huh? Got rid of anything that wasn't bringing joy or serving a purpose?
Exactly.
That's a pretty bold move, though, right?
Mm-hmm.
Like, what if they threw out something important?
You'd think so, right? But and you know what? Even after they stripped out things like the mapping network, the style injection, the noise injection, the model still worked pretty well.
Really?
Yeah, it was actually kind of surprising. The FID scores were a tiny bit higher, but it was still stable and functional.
So maybe all those extra bells and whistles weren't really necessary after all.
Yeah, it kind of suggests that, those additions, they might help in some cases, but they weren't really absolutely essential to the core functionality of the GAN.
So they decluttered, got rid of all the unnecessary stuff.
Yeah.
What did they do next?
Well, once they had, this stripped down version of R3GAN 2,
Right.
they started incorporating some design principles from modern convolutional neural networks,
Well,
ConvNet,
Convets. Okay.
specifically ResNet and Convents.
Okay.
It's kind of like taking a classic car, stripping out all the old clunky parts, and then putting in a brand new super efficient engine.
Okay, I like that analogy.
Yeah.
So they modernized the engine. What exactly did they change in the architecture?
So at first, they reshaped both the generator and discriminator using this ResNet architecture with, the 131 bottleneck structure.
The 131 bottleneck structure.
It's actually pretty common in, a lot of modern vision models.
Okay.
And it really helped to improve R3GAN's performance.
I'm curious, what makes that specific architecture so effective for image generation? Like, what's so special about the 131 ResNet?
So, basically, that 131 structure, it uses these 3 convolutional layers.
Right.
And then they have different kernel sizes. So this allows the network to capture features at multiple scales, right?
Okay.
So it's like getting a more complete picture of the image.
Getting more context.
Exactly. And then on top of that, ResNet, it uses these skip connections.
Skip connections.
Which help to avoid something called the vanishing gradient problem.
Ah, okay, yeah, that's a classic neural network challenge.
Yeah. And that makes the training process much more stable and efficient.
Okay, so better feature extraction, more stable training.
Right.
Makes sense. Now, the paper also mentions something about convex-next inlying the architecture.
Yeah.
Can you tell me more about what that means?
That's where things get really interesting. They basically borrowed some key innovations from Convex, which is this cutting-edge CNN architecture, and it's known for being super powerful for image recognition.
So they cherry-picked the best parts of convex.
Exactly.
Okay, what specifically did they take?
So one of the big things they implemented was depth-wise separable convolutions.
Depth-wise separable convolutions. All right, say that 5 times fast.
Right, it's a mouthful. But basically what they do is they break down a normal convolution operation into smaller, more efficient steps.
Okay.
So you get faster computation without sacrificing accuracy.
Got it.
And then they also incorporated this inverted bottleneck design from Convex.
Inverted bottleneck.
Yeah. Yeah. So what that does is it basically widens the network at certain points, which allows it to learn more complex features.
So again, it's about striking that balance between efficiency and power.
Exactly. It's all about, getting the most bang for your buck.
Right. Were there any other, noteworthy tweaks they made to the architecture to make it more, I don't know, elegant?
Yeah. So they also simplified things further by getting rid of, unnecessary activation functions
Okay.
and using separate resampling layers. And these changes basically just made the whole thing more efficient and elegant.
It sounds like they were really thoughtful about every single detail.
Yeah, they really wanted to streamline the whole thing. But the real question is, did it actually work?
Right, like, did this minimalist, modernized architecture actually deliver?
Well, this is where it gets exciting. R3GAN, it didn't just deliver, it actually exceeded expectations.
Oh.
Yeah. So on the FFHQ dataset, for example,
HQ.
it got an FID score of 2.75, which is significantly better than the original Stylogen 2 score, which was 3.78.
Hold on, they actually beat Stylogen 2
Yeah.
with a simpler model.
Yeah. It's pretty remarkable.
Okay, color me impressed.
Yeah.
What about other datasets? Did it hold up?
It did, yeah. It consistently outperformed other GAN architectures and even some of the newer diffusion models
Okay.
on a bunch of different datasets like CFAR10 and ImageNet.
Wow.
So these results, they really show how powerful and efficient this new approach is.
Okay, this is huge. I mean, they set out to simplify and modernize,
Mhm.
and they managed to do both while also boosting performance.
Right. It's a win-win.
Okay, but let's zoom out for a second. I want to make sure we connect this back to our listener. Like, why should they care about this new R3GN architecture? What does it mean for them?
Well, I think R3GN really shows that GANs can be super powerful and efficient without being overly complicated.
Right.
And that's a big deal for both, researchers and people who actually use this tech. Imagine being able to create, realistic images, music, even text with a jam that's easier to understand, easier to train, easier to adapt.
Yeah, it's like democratizing access to this technology.
Right.
Making it more accessible to a wider audience.
Exactly. It opens up a whole world of possibilities.
So what are some potential applications? Like, where could we see this being used in the real world?
Oh man, the possibilities are endless. I mean, you could use it to generate personalized content, create these super realistic simulations for scientific research,
Okay.
or even enhance the tools that artists and designers use.
Right.
I mean, we're just scratching the surface here.
Okay, this is blowing my mind a little bit.
It's pretty exciting stuff.
Now let's dive into some of the specifics of R3GN's performance. You mentioned FID scores earlier.
Yeah.
Which basically tell us about the quality and diversity of the generated images.
Right.
But can you explain that in a way that, our listener can easily grasp?
Sure. So imagine you have two sets of pictures. One set is real photos.
Yeah, okay.
The other set is images that were generated by a GAN.
Got it.
The FID score, it basically measures how statistically similar those two sets of images are.
Okay.
So a lower score means that the generated images are more like the real ones,
Okay.
which means they're higher quality and they do a better job of representing the data they were trained on.
So it's not just about making images that look pretty.
Right.
It's about capturing the essence of the real data.
Exactly. It's about the underlying statistics.
Okay, and R3GN, it excels at this,
It
right?
does, yeah. So, for example, on the FFHQ dataset, which is all about faces, high-resolution images of faces,
Okay.
R3GN got an FID score of 2.75, which is, again, better than Stylogen 2's score of 3.78. So it's generating these more realistic and diverse faces that really capture the nuances of the real data.
Okay, that's impressive.
Yeah.
What about the other data sets? Did it keep up that performance advantage?
It did, yeah. On CIFAR10, which has all sorts of different objects, R3GN got an FID score of 1.96, which, again, beats out other GANs and even some of those diffusion models we were talking about.
Right.
So it can handle all sorts of different image types and still generate really high-quality results.
All right, I'm seeing a pattern here. But I'm especially curious about its performance on ImageNet. That's a huge data set.
It is, yeah.
It's got all kinds of different image categories. That's not an easy benchmark for these generative models.
You're right. ImageNet is a tough one. But even there, R3GN managed to hold its own.
Really?
Yeah, it got results that were comparable to much larger diffusion models.
Yeah.
Which is pretty impressive considering it's significantly smaller and more efficient.
So it's punching above its weight class, getting the same results as these much bigger models, but in a way that's more efficient and practical.
Yeah, exactly. It's like it's doing more with less.
Right. Okay, I'm loving this.
But of course, no system is perfect. There are always limitations. And the researchers were upfront about that in the paper.
Okay, good. It's always good to acknowledge the limitations. What were some of the things they pointed out?
Well, they said that right now, R3GN is mainly focused on image generation.
Okay, which makes sense. That's what they've been testing it on.
Right.
But, the possibilities beyond images are pretty tantalizing, right?
Oh, yeah, definitely. But they said, to apply this to other types of data like text or music, we need to do more research.
So it's still early days for R3GAN.
Yeah.
Right now, its sweet spot is image generation.
Right.
Are there any other limitations they talked about?
They mentioned that while R3GN is really good at, generating diverse, high-quality images, it doesn't have quite the same level of controllability
Flexibility?
as some other GAN architectures, like, StyleGAN.
Okay. Okay.
So, for example, with StyleGAN, you can tweak specific features of an image,
Yeah.
like, change the hair color or adjust the facial expression.
Right, that fine-grained control.
Yeah. R3GN, it doesn't have that level of control, at least not yet.
So there's a trade-off. You get simplicity and efficiency with R3GN, but you might sacrifice some of that granular control.
Exactly.
Did they mention any ideas for future research to address this?
They did, yeah. They suggested that maybe adding in some features like adaptive normalization or attention mechanisms could help,
Okay.
give it more of that fine-grained control over the outputs.
So they're already thinking about the next steps. That's great.
Yeah, it's exciting to see where they take it next.
Okay, before we wrap this up, I want to bring it back to our listener one last time. What's the big takeaway, the key message you want them to walk away with from this deep dive on R3GN?
I think the big takeaway here is that sometimes simplicity and modernization, they can lead to huge advancements.
Okay.
Like in this case, we saw how going back to basics and incorporating some of these modern architectural designs, it really unlocked the potential of GANs.
Yeah, I love that. And I think that message goes beyond just GANs, right?
Right.
It's a reminder that sometimes progress comes from, stripping things down to their essence.
Exactly. Finding that elegance and simplicity.
And, the journey of discovery, it never really ends. This research, it's opened up this whole new world of possibilities for GANs.
Yeah.
It's really exciting to think about what the future holds. And I want to thank our listener for sharing this amazing paper with us.
It was a good one.
It was really thought-provoking. And, to all our listeners out there, keep exploring, keep asking questions, keep diving deep into this incredible world of knowledge.
Until next time.
It really is. And, we've talked about R3GAN's performance on ImageNet a few times now.
Yeah.
Especially how it compares to those diffusion models. Can you break that down a bit more? Like, what makes that comparison so interesting?
So what's really cool is that even though R3GN is, way smaller and more efficient, it still gets comparable results to diffusion models on ImageNet. Okay.
And diffusion models, they've been, getting a lot of buzz lately.
Right. They're kind of the hot new thing.
Right. Because they can generate these really high-quality images. But the problem is they can be really computationally extensive.
Oh, I see.
Like, to train them, to use them, it takes a lot of power.
Right.
So R3GAN, it's kind of showing that there might be a more practical way to get those same high-quality results, but without needing all that, massive computing power.
So it's not just about pushing the boundaries of what's possible. It's also about making it accessible.
Exactly. It's got to be usable in the real world, too.
Right, right. And, going back to the paper, one of the things that really stood out to me was how they were able to get these great results without all those tricks and workarounds that StyleGAN uses.
Yeah.
It kind of makes you think, like, maybe they've stumbled onto something more fundamental here.
Right. Like they've uncovered some hidden simplicity within the complexity of GANs. Exactly. And it's not just about simplifying things for the sake of simplicity. It's about finding that elegance that leads to better results.
It's pretty exciting to think about where this research could lead. Like, what are some of the next steps, the potential avenues for exploration?
Yeah. What's next for R3GAN?
Well, one obvious direction is to see if they can apply this approach to other types of data.
Okay.
Beyond just images. So, could you use it to generate realistic text or compose original music, maybe even create, complex 3D models?
AI-generated novels, personalized soundtracks, on-demand virtual worlds. I mean, the possibilities are mind-blowing.
It is pretty mind-blowing.
And then there's the whole controllability thing.
Yeah.
Right, like they mentioned that as a limitation. But I imagine there are ways to, improve that aspect of R3GAN.
Yeah, definitely. So right now, it's great at generating diverse, high-quality samples.
Right.
But being able to have more fine-grained control over the output, that would open up even more creative possibilities.
It's like giving an artist a more nuanced set of tools, right?
Exactly, so they can really fine-tune their creations.
Well, this has been an amazing deep dive into the world of R3GAN.
Yeah, it has.
It's incredible to see such a big leap forward in GAN technology.
Definitely a game changer.
And I have a feeling we're going to be hearing a lot more about R3GAN and its applications in the very near future. So a huge thank you to our listener for bringing this groundbreaking research to our attention.
Yeah, thanks for sending that over.
And to all our listeners out there, keep exploring, keep asking those tough questions, keep diving deep into this fascinating world of AI. And until next time, keep learning.